monde, aussi en ligne. Donc, on est très heureux d'avoir aujourd'hui Benoi Pausader de Brown University qui va nous parler de stabilité-instabilité pour les...
Okay, well, thanks very much for the invitation. It's a pleasure to be here. And thanks for all of you for coming. I know it's been a really tough week and you had to sit on a lot of talks. So thanks for making the time. And today I'm going to present recent progress on stability and instability of small BGK waves. That is a joint work with Benoi and Benoi. All right, so if you want to be early, this is the summary of the talk. We're going to consider the Placer-Poisson system for electrons, which is PCE with a neutral background for to represent the effect of ions. We'll be in a Wanzi periodic box, and we're going to consider the stability of small BGK waves, which are of this form. And that is what I like to think of as the Smiley criterion for stability of those waves, which is that if locally around zero energy, your energy distribution looks like a smiley, then it is stable. It looks like a Brownlee space, it's locally concave, it is unstable. And then in the remaining case, we don't know, or it's inconclusive. You can notice that the case when, no. Oh, I just want. Okay. Yes, and so there was a previous result that was considering the case when the energy distribution was exactly flat in a neighborhood of zero by Go and Lin. So this is a partial complement to this. And something also that I want to say is that this follows some earlier important result by Beste and Patrick Moreno, and then more recently Beder, that take a slightly different point of view. So I couldn't really fit in the narrative later, but they also get results on the stability of BGK waves. All right. So now let me backtrack a bit and then present the problem that we will consider. So we want to consider a gas of electrons, so a lot of particles, and they obey Newton's law. So x0 is equal to v, and the acceleration is the electric field. But there are so many that we want to describe them using a particle distribution function that is then just transported along this ODE. And so as a result, this is a slightly older version of the slides. But okay, as a result, our solution is the particle distribution is transported via a Hamiltonian vector field, and this Hamiltonian vector field is just the energy, so the kinetic energy minus the potential energy, when the potential energy is obtained from the Poisson's equation. So the Laplace of E is the density of charge minus the contribution of background of fixed ions that only are here to make the medium neutral. This is indeed just a pure transport equation, but it is an equation because the term that transports them is obtained in the whole via your unknown that you're trying to propagate. So it's a self-consistent nonlinear system. And then the other preliminary remark is that you can consider periodic or localized perturbations, but either way, this has been used a lot. And by now we know that it's a pretty nice flow. And in particular, the solutions, the flow is global, dimension 1, 2, and 3. And so you have global solutions. And now what we want to start studying is the next step. So what happens? What is the asymptotic behavior? What happens as? Okay, and before we go on, I just want to share or have three principles that we're always going to follow and that inform a little bit how we approach those equations. The first one is the fact that we start from everything is transported via Hamiltonian vector field. And we really want to lean on that, and in particular to really only use things that respect the symplectic structure, axial angle variables, canonical transformations, and so on. A second point that helps, at least was good for me when to understand what was going on, is that, yeah, this is a transport equation. So as a result, your whole particle distribution function can be found once you solve the characteristics. But what is really transported is the background plus your perturbation. And so if you were to assume that you have a homogeneous equilibrium, then this is really your solution at time t. And you see that it's really the combination of two facts, of two terms, one which has to do with the excess particle that you put in initially as your perturbation, but there is also a second term that has to do with the deformation of the medium. And so this is something really important to keep in mind. There will always be those two components that talk to each other, and that there will, in general, be at least two different dynamical channels that behave differently. And finally, a third point, which is back to Landau, I think, which is that I presented you the Blaise of Poisson system and as a PD for the particle distribution, f of x and b, that evolves over time. And indeed, once you have that, then you know everything. And in particular, you can easily compute the density just by integrating f dv. But it also goes the other way around. If I were to give you the density for all time, then you would easily recover the electric field. And once you have the electric field, then you would easily solve the characteristic. And if you know the characteristic, then you know your whole solution. And so you have the choice of either tracking down a function of x and b, or just one function of x, which then lives in which is an object that is typically easier to use, even though then some part of the nonlinearity become a lot harder to follow exactly.
So it's n naught is the initial GP rate. So
in this case, it would be a homogeneous equilibrium.
And f naught is then what the perturbation.
So this is the perturbation that you have, and this is the background. Thanks for this. And to fit it in one line, I have it for a homogeneous equilibrium, so it only depends. The equilibrium would only depend on. But okay. So yeah, again, we want to try to understand something about the asymptotic behavior of solutions. And so if you think of following the roadmap of ODEs, then the idea is to try to isolate all the equilibrium, then find the homoclinic, heteroclinic orbits, and all the objects that are defined there, and then hope that the basin of attraction, and then hope that this way we fill out we describe all of the trajectories. And so to start that, we can look at steady states. And in fact, somehow the problem for Blaise of Poisson is that there is a complicated dynamic, and it's complicated in part because you have too many steady states. And so this is really I think something that is, well, makes it a bit hard to know exactly where to start. So it is clear that you have one that is simpler, the zero solution, the vacuum. But then after that, there is no clear notion of a ground state. But at least you have, in terms of complication, you have a large family of solutions, which are homogeneous equilibria, which are functions. You just need to have a non-negative function that depends on B, and that is a probability distribution. And this would give you a steady state, because since it doesn't depend on X, this cancels. Since it would create a potential that is constant in X, there is no electric field, so this cancels, and then it doesn't depend on B, so it's also an equilibrium. And then you have the last one, which is homogeneous equilibria, where you have no feature. So, and then the problem is that besides this classification, then I would not really know, what would be the first non-trivial solution that you want to study. Yes, and also something I should have said already for homogeneous equilibria, that this is a kinetic equation where we have neglected the collisions. And so as a result, it's going to be time reversible, but maybe importantly, there is no natural notion, there is no, the Gaussian or the Maxwellian is a steady state, but it's really not clear that it should be preferred. You have a lot of homogeneous equilibria, and a lot of them are important in their own right. Okay, so now if we want to look at what happens, so if we want to continue there, then the first thing to try to understand is the stability of the simplest equilibrium, the vacuum. In this case, at least you have a very simple linearization. It's just free streaming. So you don't do anything in the velocity, and then X just moves at the corresponding velocity, which is extremely simple, but it means that if you have any slight uncertainty or slight difference in B, it's really going to be magnified on the physical side. And as a result, you have a mechanism to get good asymptotic behavior, which if you're in the whole space will be dispersion. And it's the fact that if you look at a first particle distribution that is reasonably well localized in X and in B, that it evolves through that. This is always orthogonal. The uncertainty in B doesn't change, but then in X it is stretched more and more. So if you look at it in an orthogonal frame, it looks like it's tilting. And to compute the density, you just integrate vertically. And then you see that you're going to integrate something which is ever smaller. And so as a result, the low density decays over time. And so this gives you a mechanism for dispersion that tells you that something is getting better over time. Then there is a question of how do you exploit that to really fit in the nonlinear problem? And there are a lot of different ways that you can do that, using either looking directly at the decay of the density, using some kind of Strickard's estimate, using some additional vector fields, or using some kind of coordinate transformation where you can compactify your spacetime and hope that things get better. What's going to be a bit more salient for us is the case when you have a finite volume, so the dispersion is not going to help you too much. But in this case, you have a corresponding family or the corresponding side, the mirror side of phase mixing, which says that you have the same phenomenon for your density, but now it wraps around more and more. And as a result, everything is going to, or every integral in V is going to converge very quickly to its average, because you see that once the same thing is wrapped many times along the torus, then if I compute if I integrate above here or above here, what really matters is how many times I'm going to cross the face of my blob, and this doesn't really change that much from one point to the other. And so as a result, you have fairly quick, depending on your regularity, convergence of your equation to their means. And then the electric field has to do with variation of the charge. And so this is going to, so this has mean zero, so it's going to always decay quite quickly. So based on that, you could be hopeful that something is, you're going also to understand the stability of the vacuum on the torus, but somehow then the nonlinearity really kicks in and it gets a lot more complicated. And it was only ultimately understood by folding it with the next family of equilibria, which are the homogeneous equilibria, following the work of Moore and Villard. So the next family of equilibria that we can consider would be just probability in B that won't depend on X. And indeed, this is a large set of equilibrium, and their linear stability was pioneered actually by Vlasov, who tried to compare it to the vacuum, and then Landa really understood what was going on later on. And if you are in the whole space, then there is later Oliver Penrose really found basically a necessary and sufficient condition for stability. So this somewhat closes the linear question. And then the next question is, can you try to push that for the nonlinear stability of your equilibrium? And in principle, this should hold. But again, this is pretty complicated at the moment. You know, it carries over to the Lorentz equilibrium, but it's the only one for which we have any result.
Was it almost necessary?
So yeah, so it gives you a case when you can have exponential decay, a case when you can have exponential growth, and then in the middle you could have secular growth. So if so if the function 1 plus k starts to vanish, then you can have various things that happen. But it's, if you have a one parameter family, it's really only going to happen to one parameter. Okay. And what really changed from going to vacuum to homogeneous equilibrium, it's this fact that when I said, in general, you should think of solutions to Vlasov Poisson as really the superposition of two modes of dynamic. One have to do with deformation of the background. If the background is vacuum, then deformity doesn't change. But in general, you really have something else. And so And then you get to classical electromagnetism. You have charge in a medium, they move. As they move, you have some electric displacement, which is not what is going to give you the electric field, because you need to add also the fact that, okay, well, but so this is the point to your initial data created an electric displacement, but then if you have a medium, you have plenty of charges, and it's going to, the electric displacement is going to rearrange this medium, and the total electric field is some kind of combination of the two that you have to understand. And so somehow this question of stability or instability of equilibrium is really, how are the charges arranged in my equilibrium? Or are they arranged such that if I make a small movement, they will go back to equilibrium, or on the other hand, they will try to find any disturbance that I create. So you have to understand how is the dielectric effect, or how is this dielectric matrix created. This is exactly what Landau did. So the idea for a homogeneous equilibrium, then this is, you look at the linearized equation, and you want to look for an equation for the density, which is not so obvious that you will be able to do that, but if you massage it a bit, you take the space-time Fourier transform, you can really get to an, not a PD, but an algebraic equation that relates your electric displacement to your electric field via this dielectric matrix, which has to do with taking your background and then you get a combination of its Fourier transform. This is just the electric displacement. And so as a result, you see that if this function is, well, you see that this you can easily invert formally, you just divide by 1 plus k. And if you can manage to ignore the place where it vanishes, then you're all set and you have solved your linearized problem. And this is how you handle that. And then after that, you can try to go to the nonlinear, like the nonlinear perturbation, which would come in saying that it's your original electric displacement. Also, well, you have to look at not just the sum, but also the how the nonlinearity interacts with this decomposition. On the torus, you need to have something a little bit stronger than the Penrose criterion, but at least if you make sure that you can always, you have the advantage that you can ignore one mode, the constant background, or the average, and you can assume that outside of that, if you can always invert by 1 plus k, then everything is good. And in this case, basically, then you're never any worse than vacuum. And then you have to find a method of proof that works on vacuum, but this was done by the result of Mo and Villani. That says that if you have a background that is analytic, if this is verified, then any sufficiently small and sufficiently smooth perturbations is going to give you a global solution whose electric field is going to decay quickly to 0, and then you can even find the asymptotic. You can even follow your particles to limit perturbation via just linear scattering. And basically, this is the starting point. Yeah, so this is the work of Mo and Villani. Then it was also extended by Bedrosian, Masmoudi, and Wu to cover the right set of Chevret cases, simplified by Grenier and Gunn and Wodniansky. And then with Ionescu, Chusheng Wang, and Klaus Wittmeyer, we could finally get also the endpoints and also the scattering operators and all the other things about the dynamic. So somehow, if you are strongly Penrose stable, then things seem to be under control, at least if you believe that it's enough to only consider Chevret perturbations. And the goal of this talk is try to understand what happens when this is violated. And so to understand, well, first, and this is where we're going to see what works and what doesn't. But this, I just want to show you a video of the good case, what happens in the good setting. And so now we're going to have the problem of the, so this works, and now I need to share, and I share QuickTime. Okay. And now let me just do this. And so you see this on the top, this is about distribution, and you see what we saw corresponding to the phase mixing. This is your electric field and you see that it very quickly. In this case, I'm just showing the perturbation of the Maxwellian. But things are good, although maybe you remark that, but this is not yet really well understood. This is not quite what you would get if you look at the electric field of something that is phase mixing. So the medium, a non-trivial medium, is going to add in the plasma rotation, plasma frequency that makes your electric field also rotate over time. But things are good, and if everybody decays exponentially, then you can, it's good enough.
So,
Yeah.
So it's the electric field, but associated with the given.
This is the maximum of the electric field.
Maximum.
Yeah. So maybe this is the maximum of the electric field. If it was just the mode that is oscillating like e to the it, that you take the real part, then it should exactly go down all the way to 0 at some time. But there is another mode that is created by the phase mixing that is that is usually decays faster, so you don't see it. But when the first one cancels, some people then come over. So you get to see that trace also. And this is the fact that the bottom is a little bit here and there. And in fact, maybe for Maxwellian, you have several modes that oscillate. That I don't know. I'll have it under control by the end of the talk. Yes. All right. So one way that I like to understand where we're trying to go is the fact that we're against this Penrose function 1 plus k, and this is an old result that was even before Penrose from Landau, that if you're looking at an equilibrium that is just monotone decreasing, then it's always stable. It's going to be always, so this 1 plus k is always non-negative. So Maxwellian is okay, and this is the natural setting for the type results. And then what Penrose added is the fact that, as you can see here, you don't need to be just linearly decreasing, especially even on the whole space, but especially on the torus. Then you can have some dips, but if they are not too bad, that doesn't really matter too much. And so here I've given you a case when you can really do all the computation explicitly by doing some partial fraction decomposition, the generalized Lorentz equilibria. And in this case, the 1/3 is the one where that delimits the stable and unstable. So all of those will be stable, and including ones that have a tiny dip, but if the dip is too big, then they're stable. And at least the Muro-Villani result doesn't really work. So I like the general Lorentz equilibrium because you can really do all the computations by hand. But basically, what you should think of is that they're part of a bigger family of equilibria, which have to do with, so if this is always stable, then the next thing that you would want to understand is what happens if I have two bumps. So the so-called two-stream equilibrium that corresponds to having half of your particles going more or less at the same velocity in one direction and the other half of the particle going at different velocity. So in other words, you look at distribution functions, which would be a Dirac mass at, say, +1 and -1, but Dirac mass is a little bit too harsh to really make sense, but you can flatten that a little bit, and the moment you flatten it, then you have equilibria that looks like that, two beams. And you can see that in general, it's going to be the same phenomenon. If I flatten them too much, so this is if I have two Gaussians, because the next video is going to show you what happens with two Gaussians. If I flatten them too much, then I just have an equilibrium. It's hard to see the difference between this and just one Maxwellian. But as my scale here becomes smaller and smaller, then they start to approximate more and more to half Dirac masses. And you can try to, and so our talk, or our result is trying to understand what happens in this case. And this is an older, now things are better. And so in this case, well, let's see what happens. These are peak simulations of exactly this case. So these are the equilibrium. I've chosen, I think, 2 million particles, but can only show 10% of them. But these are taken randomly according to the law of the two-stream. And so if my two streams are very broad, then this should be stable. And as I make them more and more well-defined, then it should be more and more unstable. And we'll see what happens here, because I'm trying to say that it's not just about the particles, it's also about the information of the electric field. And I also plot the electric field corresponding to the two extreme cases, this one and that one. And this one, well, it should satisfy the rule setting. This is not quite analytic perturbation. No, it's not so necessarily so small, but hopefully things will still be okay. And you see that, well, in this and this one as well, very quickly, exponentially, everybody goes to zero. And this is an equilibrium. If I look at here, then I more or less have a constant density of particle because they are at a given velocity. They move in phase space, but that's the definition of an equilibrium. Whereas in the other cases, then actually maybe this one is also unstable. But in the other cases, then something really different has happened. And in particular, you see that the electric field, at least it has a pretty well-defined shape, but it doesn't really go to zero. And so, well, what we would like to do is to understand what happens in this situation. All right. So, what are the bifurcation? Well, you can think that if the Moore-Villani criterion was the right one, then something should really happen at the edge of some of the hypotheses. And indeed, what you can see is that, so it was this function 1 plus k that was supposed to never vanish. You can see that it should vanish in our case when we look at symmetric perturbation of 2 humps. It should really start to vanish at the lowest mode and at the frequency 0, which corresponds to the thing that something dramatic should happen around here. And indeed, in this case, you can do some local bifurcation to see that at my family of homogeneous equilibria, there is now a bifurcating or emerging from that a family of new steady states which are homogeneous. So now they will depend non-trivially on X. And yeah, so I start to create the nucleation at the edge of the Moore-Villani criterion, nucleation of another family of steady state with some good critical bifurcation so that the stability goes to them. And you can also see that, yes, and just by the fact that you construct them via local bifurcation, then something has to do with some element of the kernel of your operator, and the net result is that the electric field is always going to be in the direction of the eigenmode of your Laplacian on the torus. So it's always going to be a small multiple of cosine, and then there's another perturbation that you can solve, but that is of size which is then much smaller. And not just that, but you can see that the moment, well, basically by definition, the moment you create any curve of steady that is sufficient of steady equilibrium, it really has to go through that channel. And basically, this is really going to be what's going to make everything work for us. The fact that we have a lot of different equilibria. They're all very different, but at least in the limit of small BGK waves, then their electrostatic potential, they all kind of look alike. And so now maybe we can try to handle all of them.
They are regular.
Sorry? Well, we'll look at this. This is up to you.
You choose the regularized class and then you solve that.
Yeah, you can do a bifurcation in C2, you can do a bifurcation in C3, you can do a bifurcation in CK. But there is more to it than that. But let's just get to this quickly. But at least if you do it this way, then you will create what is called a one-well BGK wave, which is a function of the energy, which is of this type. And if it's of this type, then again, we always want to look at the density or the electrostatic potential. And in this case, the Laplacian of the electrostatic potential is the density, but the density is what I have when I integrate this dV. And so it's really just a function of my electrostatic potential. So bottom line, this guy needs to solve an autonomous second order ODE. And so as a result, it basically can only have that form. If it has a maximum, then it has to be symmetrical across the maximum. If it has a minimum, it has to be symmetrical across that minimum. So it just goes from maximum to minimum and then continues. And so, yeah, so long as they're of this form, then the potential has to have this form. And you see, it's more or less, I guess it's plausible that it's going to start being a cosine and then maybe getting a bit more deformed as f varies. Okay, so that's a first thing to keep in mind, and that's kind of interesting. You have, at the point where things break down, you have inhomogeneous steady states, but they all have the same, basically, electric field. On the other hand, this seems a bit at odds with an old result of BGK that gave the name of BGK wave, which was more or less an explicit parametrization of the set of all steady states, at least the set of all one wave steady state of class of Poisson. And that said, as we, so then, okay, there is the regularity criterion, so you can put some other integers there, but basically it says that so long as I can choose any distribution of free electrons, I can choose any potential that goes from maximum to minimum monotonically. And there will be a BGK wave that has this free distribution and this potential. Well, so if I want it to be continuous, I have to solve one linear relation, but it's C2, C0 cross C2, and then I take a hyperplane over that. It is a very, very big space. And in particular, it looks like I can choose this guy completely freely. Yes. So this is the thing now to go in the direction of your question. There is something about the regularity. So for example, I need one linear relation for every matching condition. So with this, I can guarantee that it's going to be, I think, C1 1/2. If I wanted at least C2, then I will need to have another condition. If I wanted C3, another condition, etc. And then there is also some kind of little bit of care that has to be taken in terms of the right spaces. And this at least took me a long time to really appreciate that if you want some C0 alpha, then your second derivative should be in something that, so it should be 1/2 more regular, maybe wide, but not just that, it should also make sure that at the place of maximum and minimum, it also gets, technically it's also C2 at the places of maximum and minimum. So you need to, at some places, have higher regularity, but more or less in the middle, it's what you want. And this is surprising, but at least, well, first BGK was here to tell us, so then it was, and they also come and give you basically a way to see, to go back and forth. And also maybe to understand why there is this kind of slightly, so a BGK measure is not a general measure, or in the sense that it's a C2 measure, but, or let's say C0 measure, but such that if I integrate it along a line, then I get something that is more regular by 1/2 derivative. So you have to, yeah, you have to see a bit what happens, but the BGK methodology, the way to understand it is that the moment you have an inhomogeneous wave, there will be in the potential well a trapped region, and what you can freely specify, and you are looking for a function of the energy. This is the phase space, it is tagged by level set of the energy. And what you can specify is the value, how the value of the energy are along this line at the separatrix, at the saddle point here. And how, so this is, what is the distribution of the, so not the level set necessarily of your function, but the distribution of its level set. So not the values of your function at the level sets, but the distribution of the level sets themselves, which correspond to the values of the velocity. And if you have that, then there is a unique way to fill in your measure inside the whole phase space as a BGK wave. Okay, so in some sense, you could say, what's the point of trying to get this nice parametrization of BGK wave. Maybe it's a bit satisfactory. But really what we want to do is going from this point. So there is a ton of BGK waves. If we want to look at stability of a BGK wave, we have to allow that a perturbation will move from one equilibrium to another one. And this, well, obviously there will be no dissipation or no dispersion in this case. I just go from one equilibrium to another. So I really need to start to do some modulation theory. And to do modulation theory, I need to understand, well, the tangent, or yeah, where can my curve of solutions behave? Now they're an infinite dimensional manifold, but at least once I have a good parametrization, I can compute the tangent space. And this is what that is this parametrization basis that you can easily compute the tangent space of the BGK wave at the BGK wave and see that they are indexed by the function and they're of this form. Yeah, and this is a good parametrization, at least if you have some elliptic operator, which is a Rayleigh operator plus some kind of one mode perturbation. If this is invertible, then this is really a one-to-one correspondence of your tangent space, except for the fact of this, the regularity, that if I take my functions that are ck, and if I take derivatives of them, then a priori there would be ck minus 1. But once so let's say this is valid for f, in this case C1, but once you have an expression like that, then it makes sense for every f in L infinity. So you can make sense of perturbations that are less smooth than your the element where you are. Or in other words, you have a ton of manifolds of steady states that are indexed by the regularity that you want. They're all included one in the other. And the tangent space have also this kind of phenomenon that the tangent space of the more regular is going to be included in the less regular, but they have linear spaces, so those guys you can understand better. Okay, and maybe this is really the picture that tries to explain what happens and what's going to make it, oh, wow. Okay, what's going to make it work is that if I choose any homogeneous equilibrium and I start varying it, then in the good case scenario, it's going to be stable. And so this function 1 plus k is going to be bounded away from 0. When it is equal to 0, which is so it's marginally stable or unstable, then what happens is that I have a curve of steady states, but in fact, I have a lot of curves of steady states that originate from that. But they all have the same, but it's a cusp. They all have one of the components. The free part is completely free, but the potential component, they all have to be tangent to first order here. But then what we got with this parametrization is that the moment I am inside my manifold, then I really have a good tangent space. And now I'm not forced to have the potential to be cosine. It can be any C2 function. So you really have, or maybe in other words, one thing that you can see is that the difference, all the homogeneous equilibrium and all the BGK waves are of the form f of the energy being d2 over 2, so kinetic energy minus the potential. So it's tempting to say the set of inhomogeneous case is a manifold and it has a nice boundary function, which is just the norm of phi. And it's true, but it's, well, no. Yeah, okay, but it is very degenerate because if I prescribe phi very small in, say, L infinity, but not of the form 1 plus cosine, then the other component must, or like in the top region, it must get a very big mole. So it's pretty degenerate here. But basically, this is what tells you that at least for a small BGK wave, maybe we have the best of both worlds because we're still close enough from the inhomogeneous cases that we can hope that a lot of the particles are just free and we can more or less treat them as perturbations of the Landau analysis. But we are inhomogeneous, but so long as it is small, we're only inhomogeneous in one very special way. And so now we know more or less the phase space, and so we'll be able to see how to modify our analysis. So this was just to recap, and this is the point. But made everything work for the case of inhomogeneous equilibrium is that all of the dynamical system part, all of the trajectories were trivial, just free streaming, because it was the Hamiltonian was just displayed over 2. For small BGK waves, then they're all at least 2 first order of this form, which happens to be just the nonlinear pendulum equation because it's a potential is cosine. And so that you can understand also. And not just that, but this is unfortunately only understood after the fact. This really connects to another model of Vlasov equation, which, as far as I know, arose in a different context, the Vlasov HMF model, but that now you can really easily understand as saying, I'm going to simulate my Vlasov-Poisson system, but with the knowledge that my nonlinearity has to be at least 2 first order, or to the order that matter, only along the cosine mode. So I'm going to just have the usual Vlasov-Poisson equation, but my potential, I'm going to get my density, but only the mode that is in the cosine direction. And so then it makes for a much simpler nonlinearity. But in some sense, this is really what we think happens for small BGK waves. So this is a system that has been a lot studied. And in particular, recently there were a lot of works by Faou and Bousset, and then Faou Orsin to study precisely this system, the analog of the Moore-Villani results, and even the analog of the stability of some inhomogeneous solutions. So somehow, this way you see that those two dynamics are really closely aligned. And when you have to do an explicit computation, then you can really try to go back and forth, and things will be correct to first order. So this is what this was trying to recap. Once we have small BGK waves, which are the waves that have diverged from the homogeneous solution, then we have this big matrix, but still it is bounded away from one for most of the choices of frequencies and space and time frequencies. And someplace it is not, but at least it has this unique feature that the potential is always the same. And it should be connected to calculations in another setting, the Vlasov HMF. And maybe I see that I'm running out of time, so let me just tell you that this is true. You have to understand exactly how to account for the fact that your phase space deforms, but at the end of the day, your dielectric operator, you can expand it in terms of your parameter delta, which is how far you're from a homogeneous wave, and say that your operator is going to be 2 first order, what you have for the homogeneous equilibria, which is more or less a semi-definite, or is a positive definite matrix, except that it has now a kernel at frequency 1 plus and minus 1, plus an explicit first order term that, well, to understand exactly how to think of it, you have to be a bit careful. So you will have some errors that are of this type. In L infinity, it's an expansion in root delta, but for a rescaled frequency. And so recall that to look at your equation, we'll have to take the inverse Fourier transform of that. So it's more or less the L1 norm that counts. And this is really, should be at the level of the L1 norm. So this is going to give you a non-trivial correction, but a correction that you can understand. And in particular, well, with this expansion, you can arrange, since this is an expansion, you can arrange that this is only computed for the case of exactly 1 plus cosine for your potential, so where you have exactly the nonlinear pendulum. And then this is an explicit matrix, even though it's a matrix in terms of elliptic integrals. But you really only have to understand what happens on the null space of that, because away from this guy is bounded below by 1. So with that perturbation, it's not going to matter too much. And so you basically have to understand the 2 by 2 block of this. And you see that, okay, it's going to have a 0 eigenvalue. That is just something you could not avoid because of the Galilean invariance that you have. But it's the only 0 mode, and the other one is a mode of size 1. And so as a result, you can understand the spectral properties of this only in terms of the value of the already expanded from your energy. Okay, and maybe I'll stop here, but ultimately, the result is that if this guy is negative, then you have this as a zero mode, and you can go and you can easily, and because this one pushes it down, you can find a growing mode for your equation that's going to be of root. So it's going to grow like into the root delta t, and if the E of f is positive, then it makes this integrable at least on the kernel of the set of displacement. And so long as you impose two conditions on your initial data, which is this, which is automatic, no, which is this saying that your perturbation is, you can decompose your initial data into something that is, you need to remove a big space that is going modulation mode. But once you remove it, then you have your perturbation, and so long as it is perpendicular to this Galilean mode, so x and b, it's going to the Galilean transform. No, sorry. And you can arrange your coordinates to make sure that it's going to be always basically move the same way in both, or be constant to first order, and then to second order, it's something a bit bizarre that says that if you look at the x coordinate when evaluated in the normal space, or the theta coordinates when evaluated in the action angle variables, both of them are not periodic, but their difference is a periodic function, and you integrate that, it should be zero. This is true in the case of, at least of small BGK waves, and then if you have this, then this guy is not going to be affected by the linearized operator, and this guy is going to be damped by a phase mixing in the sense that if you take the Fourier transform, it's in L2. Maybe I'll stop here.
So in the phase space diagram of the, you have the region of periodic orbits, and then you have the region of, they're also periodic because of the X variable, maybe the back force. In the middle, you have the action angle variables. They got bad at the because when at the top of the potential, the period is going to go to infinite.
Mm-hmm.
So that maybe we make some of the.
I guess at the top of the well.
Oh, okay, so yeah.
So we can go to the.
This is like harmonic potential, so the period goes to a constant. The action angle variable.
But that's so great for phase mixing if it's rigid body rotation.
Yes.
But
okay.
it's not exactly that, so it is still a little better. Yeah, but you're right.
But at the top, then you get logarithmic derivative
of the period.
And then this is no obstacle like to do the analysis on.
So somehow it's so small that it's a small enough function of phase space that it doesn't matter when you integrate. So let's see if we can see via looking at the operators. But so you have to integrate your, so this is the thing that traces when average over the orbits, and it's how the energy varies relative to the frequency. So frequency will be 1 over the period. And basically the bottom line, well, okay, so to see this, then because this is the Fourier transform, you probably want to use omega as your unknown so that you can really do a Parseval and say that the frequency, so omega should really be the right unknown, but okay. So then it means you want to understand what is dh over the omega, and in fact, 1 over omega dh over the omega as a function of the frequency. And this turns out to be something not too bad. So dh over the omega, yeah. So this guy is, and so even if I divide by this, it's, well, you do pay it. So for example, when you do your, so what's going to happen, you will have a Jacobian that pops out. So this is something very small. So it helps you. Sometimes it goes against you when you compute L2 norms. But at the end of the day, the point is that it's a logarithmic factor that you pop in, and it doesn't matter. Yeah, but yeah, this is something that is actually pretty. Anyway, at least the advantage is that you you can at least compute it exactly, or you have an exact solution for the case of the nonlinear pendulum, and then you want to show that it's always bounded above and below by that, and that's true. What did I want to say? Yeah, at least you can generalize it, and you have all kind of bizarre facts. So if you have, so for example, something that I didn't believe was true, but so I'll share it with you, is that if you have an analytic potential, so as we said, there is indeed something bizarre that happens here. And if you have an analytic potential, then your period cannot really be harmonic because holomorphic, because there is a logarithm somewhere close to 0. So this is not a pole, this is. But what you can do is expand the period as a function of this, and then times. So you need to get the logarithm. And then this guy and that guy, they are holomorphic across the separatrix, except that when you do, they get multiplied by 2, because this is one period, and then just below the separatrix, this is a half period. But yeah, it's, I guess, that if somebody has a good explanation for that, there is something associated to the Safian method, but that those guys would be holomorphic even across the separatrix, when you have to remove something that has to, not with h, but absolute value of h, so it's really...
With the regularity and the, so what I'm just wondering is, at the end, do you get like a quantitative decay rate of whatever is supposed to decay, in terms of, for the linear Vlasov case, you get exponential decay, but you get like your decay? Here you can get something similar, or?
Yes, but I don't have it yet. So what you can easily see is that because things are going to have to behave like that, then you can say goodbye to exponential decay, because at the best, your period is Chevret-2, even if for analytic potential. Okay, but hopefully it is Chevret-2 all the time. But yeah, but now you do have to contend with what happens close to those guys and how they're going to mess up your estimate. This I don't know, but at least it has been studied for the Vlasov HMF system, which is relatively similar. And the idea is that it should give you something that is always no better than algebraic decay, like 1/t². Now, does it give it to you in a direction that would be in the direction of a steady state? That I don't know yet. But just this fact, for normal initial data, you look at the evolution, they should decay only polynomially. Yeah. Yeah. And at least one way that you can see it is that close to the center, then you're talking about rigid body motion. So this is typically not giving you phase mixing. Now it is not rigid body. So the period is, the convergence to the linear pendulum is not exact. So there will be better, but
if you only have like a finite number of polynomial decay, then the nonlinear theory is hopeless, no? Or...
On the torus, yeah. So this is, but on the torus, but yeah, to go to the nonlinear problem is really what you want to ask. But so first I need to understand modulation theory in infinite dimension on that, because I will move on the variety of steady states, which is pretty complicated. So this I don't know how to do. And then also, then you, even if you were somehow able to always look at the orthogonal of that, or say you force that there is no motion in the direction of the, but like it's really non-trivial to move along the trajectory of the states, because it really changes all the characteristics on which your solutions are going to move. So yeah, but even if you were able to do that, then you probably have to face the fact that you have slow decay, and that then you need to feed that into the nonlinearity. So it's a lot of work probably for the future. And maybe if I can just say, there is another point that is a bit under contention that I'd be happy to have, or that is related to that, is I've assumed that my equilibrium was at least C1, because my criterion is about the derivative of the energy distribution at 0. Now, at least some people think that the relevant equilibrium will never be C1. There will always be a kick at the separatrix. So I imagine that if the separatrix is, so if you're always increasing, then the computation should carry over. But this is something I would like to understand. And you can take this the other way by saying, okay, I'm going to start with some unstable homogeneous equilibrium, do a small perturbation, and they should converge to a stable BGK wave. If I start with infinity data, do I end up with something that is quite nice? And it seems, so if you do it this way, this is one example, and it seems that it's right, but it's really difficult to solve well what happens at 0 energy because of all of this. And so at least with, so that this was 2 to the 12 point, like nodes, this was found a little change of slope of 0.001. So is it a numerical error or not? I don't know. But this is something that is apparently very disputed, whether even your basic equilibrium should be C1 or not. So it's complicated. And maybe to finish, but just a video of what happens in this case, if I can make it work. Okay, maybe no video then. Yeah, so, okay.